-2.
I got here something else. Okay. Yeah, okay, hold on, hold on. 1, 2, 0, 0. I got 2 here. How I got 2? It's 8, right? Yeah? 8 minus 6, right? 2.
This is -2, right?
Hold on, hold on. I'm going to eliminate this 1, 2, 0. 1, 2, 2, 4. 2 R3 plus R1. Actually, I'm going to eliminate this 2, not the other 2, right? So 1, 2, 2, 4, 1, 1, 1. I don't know where I got this from. -4. Okay, 1, 2, 2, 4, 1, 0, -3, 0, -1. Okay. 2 R3 plus R1. 2 R3. Okay. This is the wrong step here. 2 R3 plus 1. Okay. 2 R3 plus 1. So I got here 1. Then 2 plus 2, 0. Oh, you see how. Okay. I'm replacing R1 with 2 R3. Let me just do it in Scratch here. 2 R3 is 0, 0, -2, -8, right? R1 is 1, 2, 2, 4. So I got here 1, 2, 0, -4. Okay? 1, 2, 0, -4. 1, 2, 0, -4. You see, you need to do it step by step. Okay? 1, 2, 0. Sorry? Yes, please. Oh, yeah. No, this is, we said this 2 we are eliminating. Okay? This 2. Okay, so this is the 2 we are eliminating, what we did here. Now the next step here, you see, we have only to eliminate now this last 2 here. Okay. And obviously we will add it to -2 of R2 plus R1. Okay, so here -2 R2 plus R1, and this is, we are going to replace R1. Okay, so 2 and 3 remain the same. 0, 1, 0, -3, 0, 0, -1, -4. Now here, what do we end up? Let me do it again here, scratch paper. You see, it's better you do it in scratch paper. So -2R2 is 0, -2, 0, -6. and you add this to R1, 1, 2, 0, -4. This is +6, right? Yeah. Just hold on 1 second. So here 0. So I have here 1, 0, 2, right? One zero zero two. 1002. We are almost done. Here, last step here, we will just multiply this one R3 with -1 R3. And then ultimately we get the nice 2, 0, 1, 0, -3, 0, 1. And this is the so-called reduced echelon form, or also in linear algebra, it's used the Gauss-Jordan elimination method. Okay, the Gauss-Jordan elimination method, it will reduce this to this one here. As you see, we had this before when we talked about the linear dependency of vectors. It's just the identity of the vectors here, where you have the diagonal is ones and everywhere else is 0. And by the way, here it's straightforward. You will solve it. Yeah. So this means here x equals 2. This means here y equals -3 and z equals to 4. Okay. X, y, z. So bear in mind that these are the coefficients here. Which is the solution? Yes, please. This one. This one. The one to the right. It means that you just multiply the third row with -1. Yes, yes. The notation is it's just multiplying this with the constant. It's just the first row operation where you are allowed to multiply by a non-zero constant. Yeah. It's just multiplication, or if you like, just to put the dot here. I don't know, but if you put it in this, then parentheses, it's clear. Yeah. Yeah. It was correct, but I just wanted to, you know, if you are working systematically, you see, then you have here something like a hypothetical, let's say diagonal. Okay, so what I did here, I was just working first this one, then this one, then that one. Of course, you can do it the other way around. It's the same. Okay. So it's just systematic. So just eliminate one, then the adjacent, and then, because otherwise you can easily get lost in such things. Okay, it's not that complicated, but it is sensitive. Okay. Later luckily we will learn other methods to solve the linear systems. But for now, let me just, maybe at this stage, a very important note. Okay. Now I will give you a couple of minutes to start with what was A here? We started with A is 122, 133, 265. What was the last line? 265. 265. Okay. You see this matrix? This is obviously a 3 by 3 matrix. And we said corresponding to each squared matrix, there is the determinant. Can you take some time and evaluate the determinant of A? Tell me what you get. What is the determinant of A? We learned how to evaluate it, right? So this node that I'm going to mention now is really one of the fundamental things with working with linear systems. So which method are you? Are you done? Did you evaluate it? You remember we had two methods, right? The one with canceling first row, first column, multiplying by 1, then you have a negative here. Remember this method? Or you can duplicate the first two columns and then you have the diagonals, multiply them out, falling and from right to left, left to right, subtracting them. I told you guys that evaluating determinants is very essential. Actually, we're going to introduce Kramer's rule later, which is entirely using the determinants. So what did you get? -1. What did you get? -1. Okay, so it's -1. Now, why is this important? If you have a linear system in the matrix form, where A is the square matrix that contains the coefficient, and its determinant is not equal to 0, that means that the linear system has a non-trivial solution. And this is an important piece of information. Actually, it's always recommended that before you start solving any linear system to check whether the determinant is equal to 0 or not. Why? Because what does it mean when the determinant is equal to 0? That means for sure there are some of the rows that are linear dependent of each other, and which ultimately will cause the system of having a contradiction or non-solution. Okay? So if you have it equal to 0, then you have a problem. And it's a good attitude if you just check this determinant ahead. Later, we will see there is a method of solving the linear system that when I give my students the choice to choose any method to solve the linear system, they just go for this method, which is called Kramer's rule or Kramer's method. And there you are always dividing by the determinant of A. So when it is not zero, then it's possible. If it's zero, it's not possible. So that's a very crucial case here if this determinant is equal to zero. Yeah, this is an important, let's say, remark. Okay, let me check the students online if they have any comments here. Okay, they are discussing about the exam. Yeah. Okay, guys, any question? Now, slowly, we mentioned matrices very often. We mentioned the matrix form of a linear system. So let's have a closer look on matrices in the next section. What is a matrix? We defined already matrices. What is a matrix? So that's why I just this matrices. I just want to spend a section on that because it's very important. Okay. A matrix is rectangular array of real numbers, and it is so A11, A12 up to A1n. Here you have A21, A22. It goes here to some number M, and then here M2. And here ultimately you have AMN. This is called an M times N matrix. So it has M rows and N columns. So this is by default, we start with rows. Now here, this is called the diagonal here. Diagonal of the matrix or main diagonal. And A, the index Aij, where of course I is and again here the index it's row and column. Oh, sorry, this is row, this is column. So I stands, so the first number in the index stands for the row and the second for the column. And this is actually, if you think about it, is just an address. Okay, then it will be a value there. And obviously it's not commutative. That means if you have the second row, third column is different than third column and third row and second column. Okay. Now the other thing is that how to write the matrix, either we will place it in such rectangular forms where we have rows and columns, or sometimes we will be just using the notation to make it short. So you just have the IJ and then you have MN. So that means here is this one here is exactly the shortcut to the notation above. So it means here this matrix is generated by indices. I runs from 1 to M, J runs from 1 to N. Okay, now there are special matrices. There are some special matrices. Of course, if you have a matrix that you remember when we talked about this is a one column matrix, and this matrix is actually at the end of the day it's a vector, huh? It's a vector. You remember when we talked about the vectors, I told you you can just place the vector as vertical or horizontal, or it can be also a one row matrix. So as you see here, you can think about a matrix as also a collection of vectors next to each other or below each other, depending if you have the vectors. Now, who's going to tell me what is the dimension of the first matrix? Row, column. Is it n times 1 or 1 times n? Rows and columns? This one, rows and how many rows you have here? It's an n times 1 matrix, right? This is the dimension of this one. However, this one, it has 1, 2, 3, 1 row and n columns. Okay? So this is just the dimensions here. So here I have 1, 2, 3, 4, whatever, n rows and 1 column. Here I have 1 row and n columns. Okay, so far, let's take an example and see what. Any questions so far? Yes? This one? It is n. This one n. It has n rows and 1 column. Sorry? Yes, vertical. It has 1 column and n rows. So usually we agree that here. Yeah. Okay, so first coordinate is always the rows and second is column. So it depends on the agreement. Okay, so let's agree here that always row, column. So you see here 1 row, n columns. Here you see 1, 2, 3, n rows, 1 column. Okay. So a vector, you can look at it as a 1 row or 1 column matrix. Okay, and the coordinates of the diagonal is always a and n or aii, whatever you like. Now, in general, a matrix is not squared matrix. Huh? We'll see that this is, before we start with matrices have a very different arithmetic. So we will learn about the arithmetics later today. But let's just have a simple example here. So I have this matrix 0, no, sorry, 8, 0, 0, 2, 2, 3, 10, 1, 7. Just to make sure that you understand the topic. how a matrix is 0, 4, 2. Here I have 5, 2, 1, 8. Okay, so let's expand this. First question here. What is the dimension of this matrix? 5 by 4 or 4? So count the rows: 1, 2, 3, 4, 5 by 4 matrix. Okay. Okay. Who's going to tell me what is A23? A23 means small a23. That means the element in the second row, third column of this matrix. Second row, 1, 2. This is second row. Column 1, column 2, column 3 is 10. Okay. While A32, this is what I was saying, it's not commutative here in general. Third row, second item is 12. Okay. For 1, for 1 is 16. Now, A55
8.
is nothing this. Okay. So if you go beyond the range, it's it's just like if you move into if you go
Oh,
into
sorry,
a
sorry,
movie theater or
sorry.
a plane and you have a
54.
number that is not there, then you have either a fake ticket or you are in the wrong place, right? Okay, so this is now this diagonal here. Another thing regarding matrices, I just want you, even if you, when you are computing, you are studying computation, when we work with computers, mobiles, whatever, you are working with memory cells, right? So each memory cell has an address and a content, okay? And also here you think about matrices as address. For instance, this one is the address and this is the content, okay? Address and content. Another thing is here is that anyone who work with computation, anyone ever developed a program, wrote a program, code something? What? Really? Ah. No, next semester you will learn programming. Maybe group I will be teaching a group with Python, maybe. It's a double array. We call it in it's a double array. So usually to implement matrices, use the double array because obviously here you need 2 indices. So it's there actually in real life. Maybe sometimes students they have problems to imagine the let's say the real applications of matrices in life. But if you think about it, it's really there everywhere, right? For instance, let's say a typical example that's used, for instance, if you have let's say an embase, yeah, you are an owner of an embase and you have I don't know, sandwiches, meat, chicken, and vegetarian, let's say, yeah. Then you want to calculate your revenue at the end of the day or a month or whatever. Then you will be multiplying each item with how many units you sold, right, at the end. So this is a typical example of how we have or where to apply matrices in real life. When you go to supermarket, they have let's say different items, and each item they have a certain number. So this applies also the same here. Now we have some special matrices here, special matrices. I'm not going to list all of them, but the most important of them. Okay. The first thing is what we call diagonal. A diagonal matrix is usually a square matrix. It's called diagonal matrix if AII Okay, so diagonal matrix is a matrix where the main diagonal AII, it means A11, 22, 33. And notice that here it's an n times n matrix. Maybe here before we will define the so-called n times n matrix. We call it this square matrix. So a square matrix is a matrix that has as many rows as columns. We saw in general you can have a 4x5 or 3x1 or whatever, but here it means 3 rows, 3 columns, 4 rows, 4 columns. This is what we call the square matrices. Now, if all AII are equal to 1, then we call it the matrix is called, we call it a unit matrix, or I think it's also called identity. Identity matrix. Identity matrix. So usually a diagonal matrix, it's a matrix that has so here you have A and N. So this matrix here we have zeros, here we have zeros, and identity matrix we have here all ones. And here you have zeros. Okay. So this one is diagonal. This one is identity. Notice here in real numbers, we have only one identity, which is 1, right? For multiplication and 0 for addition. Here we have, for each dimension, we have identity, okay? When I'm talking about 3x3 matrices, I have 1, 1, 1, 0 here, zeros all over. If I have it 4, then I have enough different identity, but they have in common that the main diagonal is 1 and all is 0. Of course, there is the 0 matrix, which has all, even the diagonal is equal to 0. And you remember when we talked about the generation vectors? When we talked about the generations vectors, so here in this, we have the vectors here that we call the unit vectors. when we talked about the generation vector, let's say of a linear system, 0, 1, 0, 0, 0, 1, 0, and so on. Okay, so this is important. Okay, now if I have any questions, use it's clear. Okay, now here if I have if a matrix, square matrix has here other numbers than zeros, and here zeros, we call it a lower triangular matrix. And if it has here numbers, here zeros, we call it a lower triangular matrix. So depending on where you have the values, and as we saw, we had in the echelon form an upper triangular matrix where we need to reduce everything down to 0. Okay, how equality of matrices? Obviously, equivalent matrices are a topic here. Equality of matrices, if you have so two matrices with the same dimension. Of course, if they are not in the same dimension, you cannot compare them, are equal if and only if Aij equals Bij. That means here, if each element at the same location is equal to the other element. So for instance, example, if you have X, Y, Z, W, for instance, is equal to, let's say, 1, 2, 3, 4. That means here Z1, so position 1, 1 equals position 1, 1. Position 1, 2 equals position 1, 2. Position 2, 1 equals position 2, 1. Position 2, 2 equals position 2, 2. Okay. So this is the interpretation of equality of matrices or equivalence. Of course, when matrices have different dimensions, it makes no sense to talk about equality, right? Makes no sense to talk about equality. Now, another thing that is closely related to matrices is what we call the transpose matrix. What is the transpose matrix? The N times M matrix that we obtain. Usually this matrix, what we call transpose, is just flipping rows and columns, from the N times M matrix that is obtained by maybe I need just to highlight these numbers. Matrix A by switching its rows and columns is called transpose. So we will use the notation. So here mainly we will use A with a T on top of it, either small or capital, or sometimes only a bar here. So most likely I'll be using this A with T on top of it. So what does that mean here? I start with an N times N matrix. I call it A. Then I just flip rows and columns, and notice that here number of columns here is number of rows here, number of rows is number of columns, okay? So this is just switching the order. So let me just give you 3, 2.540. So let's take a matrix that has 2 rows, 4 columns, and 5. Okay, this one is, what is the dimension of this matrix? It's 2 by 4 matrix, okay? So the transpose matrix will be a, what is the dimension of the transpose matrix here? 3, 4.5. So this is a column here, it will be a row in the new matrix, okay? 2.50 for 1.20 and 5. Okay, and this is as expected a 4 by 2. Just switching the order of the elements. (1.2), this is 1.2. It's just an element. So it's if you like here, my rows here are the columns there. Okay, so I take it one by one. See, the first row 3, 4.5, second 2.50, 4. So this is 1.2. Okay. Now, as I told you, addition of matrices and subtraction of matrices. Now, addition of matrices and subtraction, just like we did with vectors, we will do it component wise. That means you will be just adding and subtracting. Now, the new thing here about matrices is the following. When we talk about arithmetics of matrices, 3 things. First of all, not all operations are defined. Okay, not all operations are defined. For instance, if you have, we talk about numbers, any 2 numbers, you can add them up. In matrices, no, they should be having the same dimension to add them or subtract them. The second, and a very important also, when it comes to multiplication, there is a rule for the multiplication exists only in a certain condition regarding the number of rows and columns of the 2 matrices. And also this is conducted using what we learned in vectors, the dot product of vectors. I hope you still remember that. Multiplication of matrices is a little bit complicated compared to other multiplications. And very, very, very important, there is no division of matrices. It's not defined. Division of matrices is not defined. However, we will find, so to speak, a trick how to come over this. If division is not defined, then you multiply with the inverse if you want to eliminate an element, because this is what it's about. For instance, if you want to make 5 to make it 1, then you multiply by 1 over 5, right? Which is the inverse, which is the same as dividing 5 by 5. Okay, so there is nothing that we call division of matrices. Now let's start with an example here that actually I took from a script of my respected colleague in Deggendorf, Professor Bob, and it tries to simplify what is meant with addition of matrices. Addition of matrices is just like, imagine you are, no, you will be an engineer, you will not an Airbus restaurant, no? Maybe just as second income generation. If you have an MBS with different branches and you are selling the same, let's say the same menu, huh? Let's make it easy. You have chicken, I don't know, meat and vegetarian sandwiches in first branch and the same in the second branch. At the end of the year, you want to make your annual, how you call it, your annual financial report, yeah? Then you will be adding the same items together. For instance, if you are sold 5,000, let's say, beef sandwiches from this location, you add it to the number from the other location, right? If you have chicken, you add it to the other, and so on. So this is how matrix actually addition is broken down in real life. So let's assume example, retailer has 2 branches. Let's call them A and B, okay? A and B. And assume that they are selling 2 different and 2 products. Let's call them P1 and P2. So in each of the 2 branches, they're sold. And this is sample of this. Okay, so let's assume branch A. And we are calculating this over a period, let's say, of 3 months. And you have here product 1, product 2. Okay, so let's assume here we have this over 3 months, let's say January, February, and March. And here we have the same for branch B. We have here the same items, say P1, P2, and here we have the 3 months. Okay, so here let's assume we have numbers here. So let's assume here 8 were sold from product 1, here 10 units, here 4 units, here 12, 5, 0, and 10, 0, 7, 5, 20, and 1. Okay. So obviously this is a matrix with 2 rows and 3 columns. So to calculate the total revenue here, the total revenue of the 2 branches, what do? We will have here the 2 products, P1, B2, and then we will be just we add up all these together. So here I have January, February, and March. Okay. So the first one here, I will be having 8 plus 10, 18. So I added the first location here with the first location. So January P1, and then I add February 10 plus 0. Then I add March 4 plus 7, 7, and so on. So this is how you might expect in real life to use. And then I have 5 plus 20. And here I have 0. Okay, so adding matrices, adding matrices is defined as, if we start with 2 matrices, let's say A is equal, let's use this notation IJ with M rows, N columns, and another matrix P. Now here I will reiterate this very important note that both must be from the same dimension. It makes no difference to talk about adding and subtracting matrices from different dimensions. Okay, then the matrix A plus B is defined as the matrix that we, if you like, let's say C here. Cij equals Aij plus Bij. Okay, so this new matrix is actually formed by adding the corresponding locations of each matrix. Okay, so here I'm adding, like here, the first row, first column to the first row, first column, second row, second column. So this location to this location. So this is what is stated here formally. Okay, and subtraction is also the same, right? Subtraction is the same. Shall we take an example here, or? So in many cases, of course, not here at university level, but with school, sometimes you might give students add the following matrices, and then students try adding and subtracting. before you start this, is this operation defined at all before you start working with that? Is it defined? If it's not defined, you can't add different from different dimensions. Okay, so shall we take an example or is it clear? Shall we take an example? Sorry? You want to ask something or just to be right? Okay. Okay. Now let's take an example maybe at this stage. So let's take A is the matrix that has 3, 5, 2, 6, 1, 2, and B is 0, 0, 1, 8, 4, 1. Find A plus B. This is the first thing. And A plus B. Okay. So let's start with the first one. Let's call this 1, 2. What is A plus B? You add 3 to 0, you add 5 to 0, you add 2 to 1, you add 6 to 8, you add 1 to 4, and 2 to 1. Okay, so what is the result here? 3, 5, 3, 14, 5. Okay, 2. Now it's a little bit tricky here. Okay, let's write A plus B transpose. What is A? It's 3, 5, 2, 6, 1, 2. Now, what is B transpose? 0, 1, 4. Yeah, definition, you make this column the first row, this second, okay? 0, 8, 1. Okay, this is transpose, of course. Now, how to evaluate the sum of these two? Is that possible at all? So this is, what is the dimension of this matrix of A? It's 3 by 2. This one is a 2 by 3, okay? So what will be the answer here? Of course, it's not solvable. No? This, if A is remains as is, so it's not possible. Okay, not defined. Not defined. It's not the same dimension, right? Okay. So this is a 3 by 2. This is a 2 by 3. So it's not defined. Okay, so let's talk about something. Maybe the multiplication here is going to be very different. But multiplication of a matrix with a scalar multiplication of a matrix A with a scalar, let's say, let's just call it K. Okay, let me just just give you an example. Let's take the first one here. 3, 5, 2, 6, 1, 2. It's just similar to vectors, by the way. Then let's say 4a is equal to. So here you will be having the 4 and you will be expanding this into all elements, okay? So 12, 20, 8, 4 times 6 is 24, right? And 4,
8.
okay?
Yeah.
You just expand this constant to all of the elements within the matrix. Now it's getting a little bit more complicated. When it comes to matrix multiplication is a little bit complicated, and it's defined only under some condition. I will tell you in short why. But as I told you, in matrix multiplication, we are going to use the dot product of vectors. So let me just remind you what is the dot product of a vector. Now it doesn't make any difference if you like it actually, vector A. Of course, here it doesn't make also any sense to just talk about dot product of different dimensions. So here they have the same dimension. And we studied this actually earlier, but this is just a reminder here of this is equal to the sum of I equals 1 to n of A I times DI. Okay, so here if you just break it down, it will be A1 B1 plus A2 B2 AN BN. Okay, again here, let's take some example before we. I'm not going to start with multiplication of matrices today because it needs time. So we're going to repeat it next week anyway. So let me just give you a couple of examples just to make sure that you understand this. Okay, so given the vectors A 12, 20, sorry, 2 and 8, vector B 1, 7, 0, and vector C equals 3, 1. Okay, then A dot B, what is A dot B? 12. Let me just put this time 1 plus 2 times 7 plus 8 times 0, right? And this is equal to 12 plus 14 is 36, right? No, 26. Now, what is A dot C? A dot C is undefined because different dimensions. Okay, it's undefined. Now, I will be uploading the script, and I want you to prepare for multiplication of matrices. Now, multiplication of matrices, it makes only sense if the number of rows of the first equals to the number of the columns, because it is defined as dot product. However, I will urge you to go to the script. I will be uploading this later today. It's about a nice example that my colleague, Professor Bob, wrote, how to understand the, let's say, implementation of such matrix multiplication in real life. Yeah, in real life. So I just took this example. You will be advised to have a look at it. It's I will be uploading a section called matrices, and the example is on page 5 of the script. So page 5 on the script of matrices. Look at the example for multiplication. I think. Okay, it's about the bakery, and it has different types of bread sorts to be delivered to different branches, and how to calculate the different the revenue at the end of the year is exactly how the multiplication of matrices is defined. Okay, so bear in mind, when we talk about matrices, before you start any operation, like in this example, before you start, you will just check, ask yourself, is this operation defined? If it's not defined, then no need to carry out the whole calculation. If it's defined, then you will just evaluate the result. So it's not always defined, the operations on vectors and also on matrices. Okay, doesn't make sense to talk about different dimensions. So now let's stop and make a small break. Then I will print out the worksheet number 6 for the students online. Worksheet number 6. Please just quiet, because we have other classes there. So, Clinton, can you hear me? You are talking about this page or the previous one? I'm sorry, I was not. This one?
No, sir, the last one.
Okay, guys online, I hope you can hear me clearly and see the worksheet here. You have it also on Highland. In this tutorial, we are going to solve worksheet number 6. Let me just say something about the first question. First question. I hope, guys, you can hear me. Let me check mic here. Okay, you should be able to hear me actually. What I'm saying is that the first question in this worksheet, we solved it already in the previous worksheet. You remember using De Morvier's theorem, and the answer was 64, I believe, right? Now here using the binomial theorem, you remember the rule for binomial theorem? Okay, if you don't remember this rule for the binomial theorem, it says the following. This is equal to the sum of six is the power here, choose I. Remember the rule for that? I equals 1 to 6. It's actually 0 or 1. 0, yeah, 0 to 6. Then I have here 1 to the power 6 minus I times, here you take I square root of 3 to the power I. Okay, so this is the rule. And 6 choose I. Maybe I write it here somewhere. You remember 6 choose I is equal to 6 factorial over 6 minus I factorial times I factorial. Okay, these are the coefficients. And here you have to pay attention when you have I to an even power, you get -1, right? No, you have I to the power 2, you get -1. Yes. Yes, there are lots of worksheets. No more worksheets? I printed actually enough, but I have here one more if you like. Anyone needs worksheet? You have more copies? Okay, so this first question we solved using the De Morvier's theorem. You remember we evaluated the corresponding polar form of this one, but here you need to apply the formula. Okay, so let's see if you get the same answer like we did in the previous worksheet. Now the second and third questions, they are actually something like solving real life problems with just like how you call it, a quiz, or try to guess some numbers or some values. And the last one here, the question number 3, you have 3 different linear equations, systems of linear equations. The first 2 with 2 variables, the third one with 1 variable. Today we learned a more systematic way to solve, in particular, this last one with 3 variables. However, here we are just trying to solve it using the basic elimination or substitution methods. Okay, even with 3 variables, with some, let's say, fantasy here, maybe you can solve it. Yeah, and you will see how difficult is it without the systematic methods that we will learn later. Okay, any questions regarding the assignments here? Anything not clear? The third question is just like you need to construct as in the second and third question, you need to construct the variables. So usually when you work with mathematical problems, you need to introduce the variables, just call the variables and then construct the equations and try to solve. Yes. Sorry? I didn't get you. What you need? Yeah. In the evening. In the evening. Either today or yeah, today in the evening. In the evening. You're welcome. You Yes. Oh, this one. Was it in the script, this one?
Not on the paper, but one of the examples that you gave.
Examples in the lecture, right?
Uh, was
What,
part
what,
of the-
what was it?
These are the three equations. Minus 3x plus 2y.
This is what we did today?
Yeah.
Yeah.
The answer that I got by solving by some other method is this.
And it works.
Yeah. If you put the value of x as 0.82 in the
This we had today, right? It's this equation, right?
yeah, this one.
Just make sure that the signs here -3
Oh.
to -6.
Plus
Yeah, yeah.
4y.
I thought there's something wrong because if there is a solution, it is a unique solution.
Because when I put these three equations in the
No,
calculator,
no,
I was
it's
getting this as the
yeah,
right
yeah,
answer.
yeah. So that's why, of course, if this
Okay.
is minus, then it's different answer.
But
Okay.
can I use the other method to?
Of course, of course, of course, of
Is it
course.
allowed in the
Of
exam?
course, here this it depends what the exam is telling you. The exam is giving you a free choice. You can use any method.
Like how is it generally? Like you ask us.
It
to
depends.
solve-
Sometimes I have specific. I'm asking for a specific method. Yeah, we'll learn 3 more methods, or 3 methods in
I
total.
solved this by a different
Substitution.
method, and I got the answer.
Okay. Okay, if it's not specifying, so here substitution or elimination are okay. Okay. Okay, number one. Anyone got it right? This one? 64, you should get. You managed to get it? Only one. You got it? Sorry? You're not finished? Ah. You maybe you miscalculated because here sometimes you see here I'm using I, maybe we use K here. Anyway, here if you have I to the power 2, it's -1, right?